Hey guys, so earlier in this unit we talked about blood, we've also talked about the heart and how that works. Today we're going to be talking about how blood flow is regulated. So this lesson is called Regulating Blood Flow. We're going to be going over some different definitions like stroke volume, heart rate, and cardiac output. You also need to know what blood pressure is and what the difference is between systolic and diastolic blood pressure. We're going to briefly go over some of the different factors that affect a person's blood pressure. You need to know what hypertension is. You need to know what epinephrine does in terms of regulating blood flow, and also how the hypothalamus helps to regulate blood flow. So first, those definitions. So stroke volume is the amount of blood pumped out of the heart every time the heart beats, and it's measured in milliliters per beat. The stronger the ventricles contract, the more blood is going to be pumped out of the heart, and therefore the higher the stroke volume. The heart rate is just how many times your heart beats per minute, and then cardiac output is the amount of blood pumped out of the heart each minute, and that's measured in milliliters per minute. So cardiac output is essentially just the stroke volume times the heart rate. The amount of blood pumped per beat times the number of beats gives us the amount pumped, the amount of blood pumped per minute. Larger people will have higher cardiac output, and if the energy needs of the body increases, like when you're exercising, that will also increase the cardiac output. In individuals of roughly the same size, the cardiac output will be equal. So for example, a 70-kilogram person will have a cardiac output of about 5 liters, and that will then change slightly as a person's mass changes. That volume will go up as a person's mass goes up. Strong, healthy hearts can pump more blood per beat than someone with a less healthy heart, so they have a higher stroke volume. That's because their ventricles contract more efficiently. They contract stronger, essentially. That's why healthy people end up having lower heart rates, because they can get the same cardiac output with fewer beats because their stroke volume is higher. Less healthy people will have a lower stroke volume. Each beat of their heart doesn't pump as much blood, and therefore, in order to maintain the same cardiac output, their heart has to beat more frequently. So heart rate and stroke volume are inversely proportional, meaning if one goes up, the other goes down. So if you have a high stroke volume, so a really effective, strong pump of the heart, then you will have fewer beats per minute, so a lower heart rate. If you have a higher heart rate, it probably means that your stroke volume is low. You're not getting as much blood pumped per beat. So try and answer these questions for a second. Just pause here and see if you can figure this out. So the first question here says, which of the above individuals is more fit or healthy? In this case, Tom and Lee have the same cardiac output, so they're probably roughly the same size. But as you can see, Tom has way more beats per minute than Lee. And this is because Lee's stroke volume is so much higher. So this means that Lee is the healthier individual. His ventricles are pumping stronger, so they're pumping more blood per beat, which is why his heart doesn't need to beat as frequently. And so what you can also do is determine your own heart rate. So the way that you can do this, if you haven't already done it, is to find your pulse on your wrist. It should be like right about here. Yeah, I can feel mine really strong right there. So kind of under the thumb and then just down a little. And then have a timer go for like 10 seconds, count how many beats you have in those 10 seconds, and then multiply it by 6. Or you can do 15 seconds and multiply it by 4, whatever, until you get a minute. And then if you can assume that your cardiac output is about 4.9 liters, which would be kind of average for like a high school age kid, you can then calculate your own stroke volume. Okay? And the way that you would do that is use this formula. Cardiac output is stroke volume times heart rate. So in order to isolate for stroke volume, you would just do the cardiac output of 4.9 and then divide by your heart rate. We get you your stroke volume. Okay, blood pressure. Here's another definition for you. Blood pressure is the force of blood on the walls of the artery. So when the blood is pumped out of the heart, it goes into the arteries right away, and that outwards pressure of the blood as it rushes into the arteries, it is going to put outward pressure on the arterial walls. That is the blood pressure. We do only measure blood pressure of the arteries, none of the other blood vessels. The arteries are the blood vessels with the highest blood pressure, and so that's why we measure it there. It's measured using a sphygmomanometer, and it's usually measured in millimeters of mercury, which is what this mmHg means, millimeters of mercury. A healthy blood pressure would be below 120/80. Blood pressure is always measured as systolic pressure over diastolic pressure, so that's why there's two numbers here. The top number is the systolic pressure, the bottom number is the diastolic pressure. The systolic pressure is measured during systole, which is when the ventricles contract and are pumping the blood out of the heart. So that will always be the higher of the two numbers, because there's a lot of pressure of that blood as it is getting pushed out of the heart and into the arteries. And then the diastolic pressure is measured during diastole, which is when the atria and the ventricles of the heart are all relaxed, so the heart isn't squeezing at all, and it's just filling up with blood. So that's always going to be lower because there's not that big rush of blood going into the arteries at that point. So yeah, this is kind of, this chart over here shows how blood pressure drops as you move away from the heart through the blood vessels. So in the arteries, the blood pressure is fairly high. It drops down as we get into the arterioles, drops lower in the capillaries, and obviously it is lower in the veins. That's why veins need those like one-way valves, because there's not actually enough pressure in the veins to push the blood back like up from the legs to the heart. So we have those little one-way valves to stop the blood from backflowing. And then the wideness of this line here is just how big the difference is between the systolic and diastolic pressure. So as you can see in the arteries, which is where we measure blood pressure, the systolic is quite a bit higher than the diastolic, again, because you have that big rush of blood getting pumped out of the heart and immediately into the arteries. That's going to bump up that systolic pressure. And then on this other chart over here, we can see kind of what healthy and unhealthy blood pressures look like. So the normal, again, is below 120 and below 80. So anything under 120/80 is considered normal. Though if you get too far below that, you can have low blood pressure. And low blood pressure isn't an issue until it gets to the point where it starts to cause like fainting spells and stuff like that. At that point, the person's blood pressure is too low, which can happen if you have like naturally low blood pressure and you get dehydrated, or if you have like a vasovagal response to something, which is the nervous system response that drops your blood pressure. And if you already have low blood pressure, kind of like at the low end of this normal, it can drop you into too low, so you start fainting and stuff like that. But generally, as long as you're not fainting, anything underneath 120/80 is good. If you are above 120/80, you start to get into the high blood pressure range. So between 120/80 and 140/90 is considered pre-hypertension. You don't really have like a dangerous high blood pressure yet, but it's getting there. And then as you get above 140/90, that's when it starts to become dangerous, how high your blood pressure is. There are a bunch of different factors that affect blood pressure. Some factors will just temporarily affect blood pressure. So if you like are exercising and have an increased cardiac output, your blood pressure will go up because of that. Arterial resistance also affects blood pressure. If the arteries are dilated, like when you are trying to, like when your body's trying to cool off using thermoregulation, that will also drop your blood pressure. That can also happen during like a vasovagal response, which can happen if you're grossed out by something. It can happen if you're in pain. All of those can drop your blood pressure. On the other hand, if your arteries constrict, that will increase your blood pressure. So that can happen if you are really stressed. It can happen when you're really cold and your body's trying to warm up, stuff like that. So yeah, that's the thermoregulation type of thing. Arteries also dilate if you have a buildup of lactic acid in your body, which again happens like if you're exercising and you start to get that like muscle burn. And that'll just be in order to increase the amount of oxygen that is available to your tissues, your blood vessels dilate so that more blood can carry more oxygen to your tissues. Hypertension is when a person has sustained high blood pressure. So it's not caused by exercise, it's not caused by a vasovagal response, it's not caused by thermoregulation. This is just like a person is at rest and they end up with hypertension, a high blood pressure. In the case of hypertension, where you have this constant high blood pressure, it can cause the weakening and potentially even rupturing of blood vessels. So it can become quite dangerous. When the arteries are exposed to that high blood pressure all the time, they can also become really hard and inelastic, so they don't like expand with like the pumps of the heart as well, which further increases your blood pressure because the blood is pushing against something that's not moving with it. Genetics can predispose someone to hypertension, though it is primarily caused by diet, especially a diet high in salt, high in fat as well. And hypertension can lead to heart attacks and strokes, which is why we worry about it. Epinephrine, which is also called adrenaline, is released from the adrenal glands anytime that you're stressed. And that epinephrine is going to cause your breathing rate to speed up so that more oxygen is available to diffuse into your blood and then to your tissues. It's also going to increase your heart rate so that, again, that blood and therefore oxygen can move through your body into your tissues so that you're ready to like fight or run away or whatever you need to do in that stressful situation. Epinephrine also causes red blood cells to be released from the spleen. The spleen is just an organ that one of its jobs is to store red blood cells. So that's also going to increase the amount of oxygen that can be carried around your body and available to your tissues. And then it also dilates the arteries that go to your heart, brain, and muscles. Again, anything that you might need in a fight or flight scenario can get more oxygen that way. It's also going to constrict the arteries that lead to your excretory and digestive system, because digestion is pretty low on the priority list when you are in like a life or death situation. So it's going to make sure that that isn't like, you know, taking any oxygen that could be better used somewhere else to keep you alive. Thermoregulation is how the body maintains your internal body temperature. Your normal core body temperature, which is like the temperature inside of your torso and inside of your head, is around 37 degrees Celsius. So it can fluctuate for different reasons. One of those is fever. Obviously, if you have a fever, your temperature goes up, and that is to help fight off the infection. Your core temperature also tends to drop at night. That is like an evolutionary trait, so that our ancestors who didn't have, you know, heated houses and stuff like that, wouldn't shiver themselves awake constantly in the night. So your body sets its ideal temperature lower during the night, so your core temperature drops. Your peripheral temperatures, which are the temperatures of like your arms and legs, can be up to 4 degrees Celsius less than core temperature and still be like totally fine and not at risk of frostbite or anything like that. And all of this temperature setting is done by the hypothalamus. It is a part of your brain that controls how your body is thermoregulating, essentially. So when it's hot, the hypothalamus tells the sweat glands to produce sweat in order to cool you down by that sweat evaporating off of your skin. The hypothalamus also tells the blood vessels in your skin to dilate. That allows more blood to go to the surface of your skin, and the heat from that blood can then dissipate out to the atmosphere. When it's cold, the hypothalamus is going to cause those blood vessels to constrict near the skin so that you don't have as much heat being lost from your body to the air. It's also going to cause shivering, which is just like really rapid muscle contractions. It's also going to cause the constriction of the muscles around the hair follicles in like your arms and stuff like that. That's why you get goosebumps. That's also an old, the vestigial trait actually. Back when we used to be really hairy, if all of your hair stood up when you were cold, it would actually provide extra insulation for you. Obviously nowadays it doesn't really do much. Like I said, shivering is the rhythmic contractions of skeletal muscles. That is also going to help generate heat to warm you up if you're cold. And there's also something called brown adipose tissue, also called brown fat, which can be triggered by a hormonal signal sent from the hypothalamus. That works best in babies as well as some other mammals, where that brown fat is able to convert chemical energy to heat energy. As adults, we don't really have enough brown adipose tissue for this to be useful, but babies do still have a lot of that baby fat, including brown fat, which is really useful because babies don't shiver. So this is one of the ways they can warm up other than shivering. Okay, that is it for today's lesson.